Hi, good afternoon, everyone. Let's continue our lesson with part of system dynamic, which is causal loop diagram. So you can open the slide in Entera about it. So last time we talked about structure of system and system thinking. I hope you still remember, right? The three, okay, the solution, yeah? So holistic integration, long-term gain, and win-win solution. Right? I hope you still remember that. So today we'll discuss about these three. Yeah? So causal loop diagram, post-process, and then stock flow diagram. Using this, especially the causal loop diagram, CLD, and FSD with this stock flow diagram, I hope you can start to model difference or differential equation in real world. Okay, let's start. So this is the review last meeting. Okay, we talk about system. There are two types of system, which is open system and closed system. What is the make it different between the two is that in open system, the past action does not control the future action. Okay, while in feedback system, the past action will control the future action, because so if we can draw, okay, a system like this, okay, this is our system, right? So always have input and output, right? So this is an open system. Okay, now if from the output you make a feedback to the input, right, through some delay, so there is some this is what is called a closed system, or feedback system. So from here, there are two types. Okay? One is positive feedback loop and negative feedback loop. So from this feedback system, there are two types. Okay. Okay. Tell me, what do you remember? What is the difference between positive and negative feedback loop? Livi.
The positive one, the positive one is that there is like the feedback.
Yeah, both of them are feedback. So we have consists of two. Yeah? Open system without feedback. The second one is feedback. So this one have two, right? So it is a positive and negative. So what is the meaning of positive feedback loop? And what is negative feedback loop? We discussed it last week. I hope you still remember.
Wait.
Okay, so when we discuss about stability, do you remember? Stable. Stable. Okay, so positive is stable or unstable?
Sorry, can you repeat, sir? Because your voice in my computer is so,
okay.
Yeah.
Let me check. Wait. If the voice is a problem, so let me make the setting. Oh, the setting is already.
Oh, your voice is quite clear on mine.
Is this? Can you hear?
It's better. there before, sir. This one, it's your voice like is kind of broken.
Okay, okay. So this is better.
Yes.
Livy, is it okay? Can you hear it or no?
Okay, now it's okay.
Oh,
Yeah.
no, it's okay. Okay, so here. Okay, so we have positive and negative feedback loop.
Uh-huh.
Okay, so
Okay.
in differential and difference equation last time, okay, we have also stability, right? One is
Yeah.
the other one is unstable, and I said they are actually the same as this. So which one is this?
The negative one is the unstable, right?
Which one? Which one is unstable?
The negative feedback loop.
No, it's the other way around.
Mm.
So the positive one is unstable. Yeah. So uh, so positive feedback loop, the throwing, this is time, right? The throwing is either like this or like that. Yeah, this is positive feedback loop. So it's unstable. Right? So while the negative feedback loop, okay, the drawing is, this is time again. Okay, the drawing is either like this or like that. Okay? So negative feedback loop is basically the one that is stable. Okay. So today, today we will create what is called causal loop diagram. So causal loop diagram, okay, is a relationship between variables, okay, in the system, okay, that you can put. Remember, system consists of many parts, right? So you have many parts. So imagine your own system. I don't know what system you want, okay, to create, and then you identify those part of the system, okay. So example, in here I will throw this is the part of my system. So A, okay, B, C, D, example. Huh? And then you will draw relationship between variables. So these are the variable in here is representing the part of the system. And then you will draw an arrow. Okay, you will draw an arrow between part of the system. Okay, you will draw an arrow if there is a cause and effect between part of the system. For example, if I throw an arrow from A to B, like this, that means A cause B. Is it clear? Yeah. If I draw from B to C, that means B cause C. So, in other words, we can say if B, then C. If A, then B. So the cause and effect here must be direct cause and effect, not indirect. Because you see, if A then B, if B then C, of course, if A then C, right? So, but because if A then C is indirect, so we don't draw an arrow. Up to here, is there any question or not? No question.
It's okay, sir.
Okay, so it cause and effect, and another way is if then. Okay, so you can say A influence B. Okay, we can say that. So now our goal is to create a feedback loop, right? So if A cause or affect B, okay, then in many ways B will come back to A, right? B is going to affect A again. So this is a circular causality that is called feedback loop. So like which one first, chicken or egg? Like that. Okay, so this is feedback loop. So eventually you will come back to A again. So you will create a cycle. Okay. Next. So what is CLD? CLD is sometimes called influence diagram. Okay. Represent the feedback loop of the system. So basically it will capture the hypothesis about the cause and effect dynamically. Okay? And it will capture also the importance of feedback in the systems. Okay. So here are the 7 steps to develop the CLT. Okay. Number 1, you list the component of the system. So any part of the system, you list them. Okay. Put them as note. Okay. Circle. And then, of course, you determine the system boundary, right? So this is part of my system, this is not. Okay. And then draw the influence diagram, okay, over the other part. So how you draw the influence diagram? You just put the arrow, okay? After you draw this arrow, okay, then you try to search for feedback loop, okay? And then you label the link polarity and loop polarity. So these 3 I will explain further. Okay, so the critical aspect here is that we are thinking in terms of cause and effect relationship, okay? So focus on the feedback linkages among the component of the system, okay? And you determine the appropriate boundaries for defining what is to be included within the system, okay? So you focus on the relationship rather than the part. You don't think of in terms of the one part on itself, but relationship among those parts. Yeah, causal relationship. Okay, remember, you are not creating correlation among those parts, but causation. And then you also need to add what is called policy variable in the system. What is policy variable? A decision variable that you can change. Okay? Policy variable is a decision variable that you can control. You can change. Okay, so any part of the system that you can change, that is the policy variable. Okay, so here is the example of causation and correlation. So ice cream sales is correlated to the murder rate, okay, because both are rise in summer, fall in winter. But there is no causation between ice cream sales and murder rate, isn't it? So this is correlation, not causation. So ice cream sales increase will increase also the murder rate. Ice cream sales reduce will also reduce the murder rate. Right? So if that is true as causation, then cutting the ice cream consumption will cut the murder rate, save life, and allow society to cut the budget for police and prison. Right? This is funny. So, but that is not true, right? Why? Because probably, okay, the causation is something like this. So the rise of the average temperature is the one that caused them. Okay, so the increase of average temperature will increase the ice cream sales. Okay, the increase of average temperature make people feel very hot and easily angry, and then will increase the murder rate. Okay, so these are the possible causation. Okay, not so. While the ice cream sales and the murder rate itself are correlated. Correlation, not causation. Is this clear or not? Okay. So, let's go to the next. So, to search for the feedback loop, okay, you think only in terms of cause and effect. Okay, then it is not enough. So what you need to do is to think in terms of feedback. Okay, that means you need to think of circular causality. So we are talking about karma here. Yeah. Okay. In time, the causality will come back to the origin. Yeah? So after some delay. Okay. So this is what is called feedback. So the initial cause ripple through the chain of causation, ultimately re-affect itself. Okay. So your goal in modeling is to search first, yeah, to have a closed causal feedback loop. Okay, so it is very important that your causal influence will be exactly those that enclose within that feedback loop. Okay, okay, I give you example. So if you work, for example, and you are uh, having salary, okay. So if your salary increase, yeah, if your salary increase, your performance will increase, right? You will feel encouraged. So salary increase performance. So this is causation. And what you will do, you will draw an arrow from salary to performance. Okay. Next, if the performance increase, salary increase or reduce. Oh, your performance increase, of course, in time. Okay, maybe some delay. Your salary will also increase. Right. So this is how you draw the CLT. Easy or not? So this is one CLT. Okay. So next, if you are tired, okay, then the more tired you are, the more you need for sleep, right? And then, and you know, if you need more sleep, the more sleep that you have, the less tired that you have. Correct? The less tired that you have. So this is another CLT. So up to here, is there any question? Can you draw CLD like this? Simple, right?
Yes, I have a question, sir.
Yeah, go.
How big can a CLD get? I mean, this is only two variables, right?
Yeah.
Can it consist like up to like more than two?
Oh, in reality, you will have 100 of variables, not two. This is simplified version.
But in the end, if we have like a lot of variables, wouldn't the causation will later turn into a correlation if it's like so big and like it will be connected, right? For example, if you connect salary to performance, if you perform better, you might be more tired. Then
Yeah.
if you're more tired, you're getting less sleep. So you can like correlate between salary and number of sleep.
Possibility is there, yes. But
Is
when you draw
it
an
still
arrow,
considered causation or correlation?
so
Yeah.
this is two CLD. Okay, in this example, you have two CLD in here. One is the salary versus performance. The other one is tiredness versus sleep. So these are two separate CLD, right? So when you ask if I do CLD, okay, based on causation, will eventually become correlation? Can be, okay, can be. But when you draw an arrow, that is the meaning of this.
Oh, okay.
Draw an arrow must be causation.
Okay.
Okay. When you talk about the whole things can be correlated, yes, eventually, right? But when you draw one arrow there, it must be causation, not correlation. That's the most important part there. Clear, yeah?
Okay.
Okay. So let's go to the next step, okay? The next step is modeling the link polarity. Okay. So here, you will add positive or negative sign at each arrowhead to convey more information. Okay. A plus is used if the cost increase, the effect also increase. Okay. And if the cost decrease, the effect also decrease. A negative is used if the cost increase, the effect decrease, and if the cost decrease, the effect increase. Okay, I will put it as simple as this drawing. The text of this explanation is in my website, so you can check there. Okay, so everything is in Revolut, so you can just check. Okay, so positive sign here. Can you see the positive sign here? Okay, this is the link polarity. Yeah. So the positive sign indicate the cost increase, the effect also increase, or the cost decrease, the effect also decrease. Yeah. What is this? Direct. Yeah. Positive sign in here represent direct, direct effect. Yeah. So negative sign, okay, in the arrowhead mean the higher cost will produce lower effect and the lower cost will create higher effect. So what is this? Reciprocal, yeah? The inverse, right? So the cost increase, effect decrease. Yeah? The cost decrease, effect increase. So how about if there is no such things, not positive, not negative? Well, don't draw an arrow. Easy. Yeah. If there is no such effect, then don't draw an arrow between the two components. Okay, you draw an arrow only positive or negative only. Okay. If there is no such effect of positive or negative, then don't draw the arrow. Clear, yeah? Okay. So again, I will give these two simple example again. Okay. So your salary increase, your performance increase, right? So if your salary reduce, performance reduce. So the sign is positive, right? Okay, after some delay, okay, your performance increase, the salary also increase, right? So your performance decrease, the salary also decrease. So in that case also positive, yeah. Can you see? Okay, so this is how you create the link polarity. Yeah? The same thing with this. Okay, the more tired you are, the more sleep you need, right? So increase in tiredness, increase in sleeping. Okay, that is positive, right? Now, how about this? Increase in sleep, increase in tired, or reduce in tired? Reduce, right?
Reduce in the, yeah.
Reduce, yeah. So the more sleep you have, the less tired you have. So in that case, negative. The sign. Clear or not? This one. Can you do it? Maybe I should give you a project, you know, so that you can create something like this, no? Okay. Okay, so this is an example. Okay. After you create the link polarity, okay, you have what is called loop polarity. Okay, loop polarity means you identify the loop first. Once you get the loop, what is the loop polarity there? So the easiest way is to multiply. Okay, you multiply all the sign of the arrow. Okay, so look at this. Okay, the more bird that you have, okay, the higher population. Okay, the higher population, the higher number of bird. Right. Now, the number of population, the higher number of population after some delay, okay, higher number of death, right? And the number of death mean reduce the number of population, so negative link polarity there. Okay, so if you look at the arrow, okay, if you look at the arrow here, you can see this is forming a loop, right? So this loop is positive multiplied by positive. So this is positive feedback loop. Okay, this is positive feedback loop. How about this? This is positive, this is negative, so this is negative feedback loop. So one system consists of positive and negative feedback loop. This is the simple example. Is it clear or not? Okay, so this is the full CLD. Okay, CLD, you're supposed to create not just the component or the part of the system. Okay, also the causal effect. Okay, and then you throw the link polarity and then the loop polarity. Okay. Now, based on the loop polarity, you can already determine the behavior of the system. Okay. Just by CLD alone, you can already decide, okay, what will be the behavior of the system. Okay. So, what is the behavior of the system? Remember, a positive feedback loop, okay, will have an even number of negative signs. Okay. That's including 0. So that means some quantity increase, a snowball effect will take over. That quantity will continue to increase. Yeah? So the snowball effect can also work in reverse. That means it can, if it decline, it will continue to decline. Right? Remember that the graph is, so the graph over time, yeah, is positive, so either going up like this, continue to increase, or continue to decrease. Yeah? It's unstable. Positive feedback loop is unstable. Okay, so it will generate behavior of growth, amplify, deviation, or reinforce. Okay, so in the CLD, you will see that positive feedback loop like this. Clear? Now, so look at the performance of this. Yeah, the more salary you have, the increase of the performance, right? So the more salary I get, the better I perform, right? So positive there. The better I perform, the more salary I get, again positive there, right? And then the more salary I get, the better I perform again, right? So that means it will create a feedback loop, yeah? Positive feedback loop. Okay, so this is exactly the arm race situation. Last time we discussed about Richardson model, remember, right? So in difference equation, that is, you know this one, yeah? The country A feel in danger will increase armation, right? And then feel B feel in danger and then also increase armation. And you will see all of these are positive link polarity. So if you multiply plus 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 plus, you will get a positive feedback loop, yeah, positive feedback loop. So the result is arm race like this, yeah, going up and up over years. See, you will know the behavior, okay, of the system, okay, just based on CLD. Clear? Yeah. So the same thing of this. Yeah. For example, you have a company. Your advertising is very good. Okay. The more you advertise, the higher your market share, isn't it? So this is link polarity is positive. And then what happened? You think that way, right? But in reality, the system must be in the feedback loop, right? So the higher your advertising money, your market share increase, right? When your market share increase, what happened? The competitor advertising also increase, right? Because they want to compete with you, yeah? So then their market share also increase, and then you feel threatened, then you increase again your advertising money, right? Eventually, you will compete to pay more and more for advertising. Eh? So this is a positive feedback loop. Eh? So competition basically will create positive feedback loop. So this is the strategy to divide and conquer. Okay? If you want to divide and conquer, you create competition. Right? Why? Because it will create positive feedback loop. Okay. So how about negative feedback loop? Yeah? Negative feedback loop will have an odd number of negative sign. Okay. Tend to be stable, balance, yeah, equilibrium, goal-seeking behavior. Okay, so over time, okay, this is the time, right? So either increase and then will stabilize, right, or decrease and then stabilize, right? Or you can have a kind of loop. Okay, you can have a loop but stabilize. So okay, cycle or oscillatory behavior but stabilize. Okay. So stable, balance, equilibrium, goal seeking. So this is the negative feedback loop. Okay. So this is the example. Okay. The more tired you have, okay, the more sleep you need, right? So the more I need to sleep. So that is positive, right? So the more sleep you have, the less tired I am. So that is negative, link polarity, right? So based on that, you create the less tired I am, the less sleep I have, right? And then the less sleep I have, the more tired I am. So what is the effect here? This is like up and down, right? So this is like up and down. Okay. So negative feedback loop can create oscillatory behavior, okay, and then stabilize, yeah, into certain value. So eventually you will stable into a certain number of hours in the sleeping. Is it clear or not? Okay. Now, can you check this? Anyone can explain this? What is the behavior here? Uh, how are you going to explain this? The more number of students, what will happen to the staff stress level? The more number,
Increase.
yeah, it will increase the staff stress level. The more number of students will also decrease the research paper published. Okay. How about this positive here? How do you explain this positive sign here? The more research paper you publish,
The higher the reputation of the university.
correct. The higher your reputation of the university. Okay. The higher reputation of university, what will increase the student recruitment.
Student enrollment.
Yes, the enrollment. Okay. So the number student recruitment increase, then the number of students body also increase. Yeah. So what is this? This is positive or negative feedback loop? This is a feedback loop, right? Come back again.
Yes.
So what is this?
It's a negative one.
Yeah, it's a negative one. So it will become stable. Okay. So then if you think about behavior, okay, the behavior must be something like this. Right? It's stable. So the number of students will increase until it's stable. So you see, using CLD alone, you can already predict. This is a tool, right? Modeling tool. Okay. I did not even put equation yet here. Okay. So based on CLD alone, you can already predict the behavior. Okay. Not really true, but at least qualitatively, you can already think of the behavior. Okay. Especially for simple system. Yeah? If the system is very complex, then you need to really put the equation, okay, to simulate that. Okay. Any question, comment? Okay. So sometimes, okay, in your system you will have more than one feedback loop, right? Especially if that particular loop of the system, okay, with more than one is actually different sign, yeah, can be positive and negative, right? So then what happen is the behavior of the system depending on the dominating loop, yeah. So the one that dominant, the one that actually will create the behavior, okay. So there is possibility that feedback loop may happen within the other loop, yeah? So that is also another possibility, yeah? So when the negative loop dominate the positive loop, then the behavior is stable. When the positive loop dominate the negative loop, then the behavior is unstable, yeah? So like this. So what do you think? This one have a positive feedback loop and negative feedback loop, right? So which one dominant? We don't know, right? Okay. If the positive feedback loop dominant, what will happen? It will grow, going up. Yeah? The population will go up, right? So if the negative loop dominant, what will happen? It will stabilize. It will stabilize. Okay. And if this is too big, okay, it will go down, to zero. Okay. So here is another example of uh, two feedback loop, yeah, positive and negative, can be depending on which one dominant. Yeah? The more knowledge that you have, the more learning that you have, the more knowledge that you have, right? So this one is, when you learn a lot, you get more knowledge. Yeah? And then, of course, the more knowledge that you have, you are encouraged to learn more because you can read better books now. Yeah? Okay. Now, at the same time, okay, the more knowledge that you have, the more you forget, right? So the more you forget, of course, the less knowledge that you have. So this is the forgetting part. So this is the positive and negative feedback loop. Now, depending on you, yeah. So if this is dominant, okay, then your knowledge, the level of knowledge can go up. Yeah? If the forgetting part is dominant, then the less knowledge that you have. Okay, so in reality, probably the system is more complex than just two or three parts, right? This is just a simple example, okay, of a biosphere, okay? So evaporation will influence the cloud will influence the rain, the rain will influence the amount of water, and then eventually will influence the evaporation. That will create a nested feedback loop and so on. So from here, you start to what you will do here. You will put the link polarity. Yeah, you put the link polarity like this, right? And then after you put link polarity, what you will do, you will check the loop polarity. Yeah. So you can see here we can create both are negative loop here, and there is a positive loop here. Right. So there is a positive feedback loop there. Can you see? Okay. The more sunshine that you have, the more evaporation. Yeah? The more evaporation, the more cloud. Okay. The more cloud, less sunshine. Right? Less sunshine. So this alone will create a negative feedback loop. Okay. The same thing here. This will create a positive feedback loop. Okay. And here, the amount of water and evaporation will create negative feedback loop. So you see, the real world model is more complex than that earlier that we have. Is it okay? Do you have any question? Can you make something like this? CLD, causal loop diagram. Can you make it? Okay, so sometimes you have exogenous items. That means the item that outside the system. Yeah. For example, the sunlight affecting the plants, right? And then it will increase the density of the plant. Okay, this is a negative feedback loop. But the sunlight itself is actually external item, so we call it exogenous items. Okay, so nothing will come back to the sunlight, right? So there is a possibility of this kind of system. So again, delay apparently play a very important role in system dynamic. Yeah? By itself, a delay is actually one level or two levels. Yeah? Sometimes three levels. Later, yeah? We discuss about levels. So delay will create the system response sluggishly. Okay? For example, in the example below, okay, once the tree are planted, the harvest rate can be 0 until the tree grow enough to harvest. Right? So the more you plant the rate, the higher the planting rate, yeah, the number of growing tree will become higher, and then the harvest rate will also become higher. Yeah. The higher your harvest rate will reduce the number of growing tree. Right? So this is a negative feedback. But there is a delay. Okay, so there is a delay between growing tree to the harvest. Okay, so this is just tips. Yeah. So when you see a double arrow, yeah, probably okay, there are more variables inside that you have not specified. So you need to add more variables probably. Huh? So and then as much as possible, try to select variable that can be measured quantitatively, as much as possible. So, and then the influence should be able to measure with direct effect, okay, whether increase or decrease. Yeah? Indirect effect means there is some lack of variables in between. Okay. So I'll give you a case study. Okay, so this is from Professor Gunther in University of Klagenfurt in Austria. So we will use CLD, okay? And then given this model, what action do you think we should suggest? Yeah? So here it is. Anyone want to explain this? So tell me, which one is the policy variables in this system? What is the policy variable? The thing that you can control. Okay. Very important, right? To know which of this system that you can control.
We can control the police activities since they are like from the government, so we can control them.
Correct. That's correct. Excellent. So now the higher police activities, what will happen?
They can
heroin.
Heroin.
Okay, what is the meaning of this plus here? The higher police activities will
more heroin will increase the heroin secured by the
increase heroin secured by the police, right? And then when you increase the heroin secured by the police, what is this? We'll have less heroin in the market, correct?
Yes.
Okay. When you have less heroin in the market, okay, the criminality of the addict decrease.
Yes.
In the beginning. And then the criminality of the addict decrease, then less police activities. Right?
Yes.
Because less police activities, then the heroin in the secured by the police also decrease. Okay? If this is decreased, then the heroin in the market increase. Yeah, you see that the loop, right? This is because this is negative feedback loop, so you can see that kind of oscillating behavior. Okay, the same thing. If the heroin available in the market increase, right, the heroin trade is also increased. Okay, and then the number of addicts who deal with heroin is also increased, right? So again, because of this negative part here, you will see this is all negative feedback loop. The same thing with this loop, you have a negative feedback loop, right? So we have 3 negative feedback loop in this system. Okay. So now look at the okay. So policy activities is the policy variable. Okay. So look at this is what is called price elasticity. Yeah? So the heroin price elasticity is something like this. Okay. So what does it mean? Okay. Say if you have 10 kilogram of heroin available in the market, okay. So say the price is $1,000 per kilogram. So and then you get 10 revenue. Okay. Now, if you the police secure heroin in the market, right? So now become 9 kilogram, okay, and then the price become 2,000. Okay, now the price become 2,000. So this one multiply, okay. So the revenue become 18. But this is counterintuitive, isn't it? Huh? Because of this non-linearity, okay, the more secure heroin by the police, meaning the police activities, will actually increase the revenue for the drug dealer. Correct? So actually, the police activities, okay, increase the revenue of the drug dealer. Right? So there is something problematic in that earlier model. Okay, what? They did not include heroin price. So now the way you model is like that. Okay, you have a version 1, now you have version 2. Okay, now this is the version 2 CLD. Okay, when you put here, okay, suddenly you will see that look, this is actually positive feedback loop. When you have a negative feedback loop earlier, so the problem is actually the police activities will actually increase. Okay, if you look at this, yeah, the police activities, okay, will actually increase the criminality of the addict. Okay, this is positive, right? So be careful, okay, when you do a modeling with CLD. So you see, earlier is negative, now it becomes positive. Can you see that? Okay, so what is the lesson? Yeah? So the lesson is CLD, yes, it's very useful tool, right? And it can help to discuss the situation, even though we are just discuss qualitatively. Okay, so when you have a different point of view, you can clarify, you can check more easily. So this is really a good model, right? And look at the same situation can be modeled in different ways, right? So it's not unique, right? And that different ways is actually depending on the model assumption, okay, the one that you assume. So sometimes we need to discuss our assumption, okay, and look at this very small difference, just one more part, which is the heroin price a while ago, okay, will make a very serious consequence, okay, to the model. So from negative feedback loop suddenly all become positive feedback loop. Yeah? So what appeared to be the solution at first, right? So is actually become the problem, right? So at first you think that, oh, police activities is actually reduce the heroin. Yeah? But when you add the price, then you suddenly realize that this is not true. Okay? That actually we increase the problem by having more police activities, because this is actually positive feedback loop, not negative feedback loop. Okay. So yeah, so basically CLD is a qualitative model. So, and you can explore the anticipated side effect. Okay, identify the performance, and eventually you can check, okay, the behavior, unless if you have some loop that is dominant. Okay. So up to here, is there any question? Can you make a system and then you create CLD of it? It is something interesting or not? Okay. Very simple model, just plus minus. And then from the plus minus alone, you can already create some behavior. Now, the next lesson, we will use that CLD. Okay, we will create a very simple model, okay, of difference equation. Okay, we will create a simple model of difference equation based on that causal loop, and then we will be able to create behavior. Yeah, we can draw the behavior in Excel or using paper and pen. So before this new topic, so is there any question about CLD? Divi, Joy?
All good, sir.
All good, yeah?
No, all clear, sir.
All clear. Really, yeah? You can make... Okay, so I assume at this point you have your own CLD. Okay? So let's call this CLD part V1, V2 until Vn. Okay? And you have causal relations between the two. Okay? Now we are going to create a simple mathematical model in a network. Okay? So, so if your variables list is too large, then you need probably to consolidate. You probably want to combine those variables that behave similarly, or you want to eliminate. Yeah. So if the variable that actually no effect or very little effect to the behavior of the system itself, you probably want to eliminate. So time is discrete because we are doing difference equation here. Okay, so we will look at the status of the system at discrete time. Okay, the unit can be hour, second, days, weeks, whatever, decade, yearly. So it's you who decide the actual time unit. Okay, and then you just take the smallest unit time to produce the change. Now, we are more concerned about the change. Okay, the change, increase or decrease of the value of the variable rather than the actual value themselves. Okay, the value can be utility in here. So it's not really important what is the number, but it's important whether it will increase or it will decrease. Okay, so to know such value can be found if one is so desired is sufficient. So it is not important to how such value can be measured accurately. For example, you don't know how to measure utility, right? You don't know how to measure love. You don't know how to measure faith. Okay? But you can put those love and faith into utility. So you know it will increase, you know it will decrease. Ordinal value. So that is enough. Okay? So even if you cannot measure accurately, you can actually know, okay, whether it is increase or decrease. So let's assume, okay, this is a very simple, simplified model. Let's assume there's a pulse. Yeah, the pulse can be increased or decreased in one of the variables at time t. And that pulse will lead directly to the increase or decrease, that means increase and decrease, meaning another pulse, in some other variable at time t plus 1. So what we want to know, what will be the effect over time to the system. Okay, again the same thing, yeah. So we have two possible relationships, which is positive and negative. Okay, the positive here is an increase in Vj will lead directly to the increase at Vi will increase at Vj at one time period. The same thing with negative. Negative will increase in Vj lead directly to decrease. Okay, so negative means reciprocal, yeah? Inverse relationship. So cause increase, effect decrease. Cause decrease, effect increase. Okay, the same as CLD, right? This is just the same as CLD. Okay, so if you have no relationship, if a pulse at Vi at time t may cause no direct change in Vj at time t plus 1. So if there is no link, okay, there is no arrow, that means there is no pulse to change. So don't put any line or arc or arrow from Vi to Vj. Okay, so what we will do, okay, mathematically this is called directed graph. Okay, so if we put each variable as a point node, okay, and then the arc, the arrow connecting the pair of points indicate direct relationship, okay, then the set of vertices and the arc is called directed graph. So sometimes we call this D graph, meaning directed graph. Okay, now in each arc may be thought only as positive or negative. So in here we have what is called sign D graph. Okay, so from the sign D graph you can create matrix. Okay, so this matrix is a square matrix, adjacency matrix, okay, with a sign. So the M, matrix M, okay, we call this Aij. So is equal to 1 if there is an arc Vi to Vj with positive sign. Okay, is equal to negative 1 if there's an arc Vi to Vj with negative sign. Yeah? This is positive sign, negative sign. And then if there is no arc, you put the matrix Vij 0. Okay, so now the sequence of vertices connected by the arc is called path. Okay, so simple path, yeah, if these vertices are distinct. Okay, now if the beginning and the end is exactly the same node, okay, so this is called, the path is closed. So the simple closed path is called a cycle. So basically what we want to do is to create a feedback loop, right? So that means in the graph theory terminology, we create a cycle. Okay? So a loop is basically a cycle. So a loop in the sign graph indicates that the pulse at that vertex lead directly to the new pulse at the same vertex in the next time period. Okay? So because there is a sign, positive or negative, so we just count. Okay? We count every positive as positive, yeah, and negative as negative. Okay? At this point, we just count. So, and from there, we can check, okay, the loop polarity, whether it is a positive cycle or negative cycle, right? This is positive feedback loop, so augmenting cycle. Or a negative cycle we call also inhibiting cycle. Okay, oscillating effect. Remember, this is exactly the same as CLD a while ago. Okay, now what you need to do is to trace the sign. Okay, so we put a trigger pulse at Vi. either increase or decrease. Okay, and then you trace the sign of variable Vj, okay, at time t plus 1, t plus 2, and so on, using this kind of sign. So positive mean increase, negative mean decrease, zero mean no change, okay, plus plus mean two are contributing increase, plus minus mean two are contributing increase and decrease. Because we don't know the actual increase and decrease, okay, we just accumulate the sign. Okay, let's stop the talking. Let's try to do it with example, numerical example. Oh, we have 4 nodes here. Suppose we have this system, okay, with all this link polarity here. My question, can you make an adjacency matrix of this? You can just draw here, or you can make your own whiteboard. Can you create?
Can we annotate?
Yes, you can annotate.
Okay, wait. We make a matrix.
Oh.
Okay, wait.
Okay.
Oh.
Okay. So 0 no need to put. So just positive and negative. Okay. So V1 to V2 is
1 positive.
yeah, positive 1. So you just put
V1 to V3.
okay. Correct.
If no arrow, it's 0, right?
Yeah, if no arrow, 0. And then V1
Oh.
3 is there, nothing, so 0, right? V1 to V4, nothing, so 0. Okay, and then V2 to V1, so 0.
V2 to V3 minus 1.
Mhm.
Oh no, why is it messed up?
Okay, so V2, V2, 0, and V2, V4 is negative. V2, V4? There is no V2, V4.
Wait, it's messed up. I just draw.
Okay, you just throw.
It's very hard to annotate. So wait, so V2 to V1 is 0.
Mhm,
V2 to V2 also 0.
mhm.
V2 to V3 minus 1.
Minus.
V2 to V4 0.
Okay, very good. And then
V3 to V1 0.
three.
V2.
V3 is only to V4, so 0 again, and then that one minus 1. Very good. And then V4 to minus 1, correct? And then that one to V2, that is what? Positive 1. Yeah. And then
Okay.
very excellent. Okay, so you created the adjacency matrix, yeah? So based on that adjacency matrix, okay, you can make. Okay, so is it the same? Right. Yeah. So yeah, this is from, and then that one is 2. From row to column. Yeah. Okay. So next, once you make that adjacency matrix, you can also identify the cycle. Can you identify the cycle? Can you identify the cycle? How many cycle? Leafy, can you identify the cycle? And then check the loop polarity of that cycle. Yeah, this one is a drawing.
The first one, V1 to V2,
and then
positive, and then V2 to V3, negative. So negative, and then V3 to V4, it's negative.
And then come.
And then V4 to V1 is negative, so it's negative.
Negative feedback loop, right?
Loop.
And then any other
negative
cycle?
Feedback.
Is there any other cycle?
Yeah.
Where? Cannot, right? This is not a cycle.
Yeah, V4 to V2.
V2, okay.
Positive, and then V2 to V3 negative. V3 to V4 it's negative. So it's negative feedback loop also.
So this is a positive, right? Because negative multiplied by negative.
Oh, yeah, negative by negative. Yeah.
So
it's positive.
It's a positive, yeah. Okay, very good.
Mm-hmm.
So now, based on that, okay, this is how you simulate, okay. Look at this. This is the drawing, okay. I will start to simulate, okay. At time 0, I will add, say, this is my assumption, right? So I will add 1 pulse positive in V1, okay. In t time 0, I will add 1 in here, positive here. What will happen? In time t plus 1, what will happen? This 1 will move here, right? This positive will propagate, yeah? It will move here. So become what? So become positive in V2, right? And then at time 2, what will happen? This is now positive, okay? At time 2 will become from here to V2 to V3, what will happen? This is negative, right? So this positive multiplied by negative will become negative. So at time 2, V3 become negative. Can you see it? So V3 become negative, right? And then multiply by negative become positive, right? So the next time step, with this time 3, now become positive in V4. Is this clear or not? Now be careful here. Now we have positive in V4, but V4 has 2 branches, right? So what happened? The next time step, it is time 4 in here. This is positive, go here, become negative here. Okay? The positive here, go there in V2, become positive. Can you see? Okay. Now things become more complex, right? So in time 5, what will happen? In time 5, look, this V1 will influence to V2, but the influence is positive, so that negative will remain negative in V2. But earlier V2 was already positive, right? This V2 positive will go to the V3, yeah, negative here. So can you see that or not? So now you can start to see the behavior of V1, V2, V3, V4 over time. Can you do it clear or not clear? Super simple. Okay. Okay, if you are thinking this is super simple, can you continue that time 6, 7, 8, 9, 10? Okay. So maybe you can use Excel. It's up to you. Once you finish, you show. Okay, you share your screen. I'll post the recording. Let me. So let's put back. So V2 in time 5 is negative.
Negative.
Right?
Mm-hmm.
So here the negative part will go to time 6. This V2 will go to V3. So times negative become
positive.
Okay, so this one
Mm-hmm.
can become positive here. Okay.
Yes.
V3 is already negative, right? So
Mm-hmm.
2V4, okay, negative.
It's negative.
It become positive. So this one becomes positive. Okay. So and then V3 become negative.
Negative. Yeah.
Is this clear?
Yeah.
How about Joy? Let us see. Oh, she disappeared. Okay. Maybe the connection. Okay. So you can make it, right? You can continue this, right?
Yeah.
No yeah. Okay. So there is a problem with this model, right? So what? This is only talk about increase or decrease, right? But we don't know the magnitude of increase or decrease, right? It will grow smaller or grow bigger each time? We don't know. Okay. So how to solve this problem? We need to improve this model. Okay? This is only sine diagram, right? So that is basically CLD plus, right? So we will improve this model with adding weight. Okay, so this is the model improvement of the sine graph. Okay, why? Because it's inadequate to answer the magnitude of the poles, right? So a better model, so let's make a poles graph model with certain weight. Okay, that weight is based on the adjacency matrix Aij. Okay, so instead of -1, 0, and +1, now we can put any number. So we can put any number in the W. Okay, so when the VI, okay, when the VI is increased by W unit at time t, okay, the connected vertices Vj will increase or decrease by that W multiplied by Aij. Okay, so now we put weight in the link. Okay, W. Okay, so with this we can calculate the pools in linear fashion. Okay, so in that case, our D graph, okay, now become like this, weighted D graph. Okay? So the adjacency matrix is now become weighted adjacency matrix. Okay, with Wij, okay, can be any value, right? Can be any value, and can be positive, can be negative, can be 0. Okay, so in that case, the sine D graph a while ago is actually a subset of this weighted D graph, right? Okay, so for our purpose in this study, we need what is called initial value. Okay, so we want to study the change in the value variable from the initial value is not the actual value itself, right? So let's assume that initially it starts with 0. Okay, otherwise we must initialize its variable at time 0. Okay, so for our example, okay, we will use this. Okay, we will use this one. So you see the weight here. For example, V1 to V5 is negative 1.1. Right? So V1 to V2 is positive 0.3 and so on. So do you think you can make the adjacency matrix of this? Yes or no? You want to try?
Yes. Yeah.
Okay, let's try you make the adjacency matrix of this and then you show me. Can you?
Okay. Okay. One, two, three, 5. Do you want me to share my screen or
Yes,
what?
please share your screen.
Okay. Here is the adjacent matrix. So this one is
3,
0,
1, 2, and T 0.1, 2. Okay.
Yeah.
Very good, very good.
This one.
Okay, very good.
Yeah.
Okay, so you will use this. After this, you will. Okay, save it. Okay, because you are.
Okay.
That. Okay, you're going to use that. Okay, so okay, is Joy there already? Yes. Joy, we just go to the next system, which is weighted T graph. Okay.
Yeah.
So it is exactly the same, except now we put instead of 0 and -1 and +1, we can put any number as the weight.
Okay. Yes.
Okay. Okay. So let's go again to the slide. Okay. So you need to create the adjacency matrix. Okay. Because we are going to use that later. Huh? Okay. So a little bit different from the sign the graph. At this point, you will retain the value. Okay, the pulse is put, and then you will retain the value of the pulse. Okay, the difference between the signed graph and the weighted similar graph is you will retain the value of the pools. Okay, let's say here at time 0 we created these new pools in V1. Okay, and what will happen? Okay, look at the graph here. So if I put 1 in here, then at time 1, what will happen? This one multiply 1 multiplied by 0.3, right? So V2 become 0.3. How about this one? 1 multiplied by negative 1.1, right? It will go to V5 negative 1.1. Okay, but earlier in sine graph, this one is 0, right? Come back to 0. But this one retain. Okay, it will retain continue 1. Okay, and then what will happen? Okay, again at time from 1 to 2 now, yeah. So at time 1 we have these numbers, right? This is the pools, the amount of the pools. Now at time 2, the V1 go again to V2, right? With this multiplied by 0.3 again, correct? And then what happened? Now before it has 0.3 here in V2. So it will go to V3 and V4, isn't it? So 0.3 multiplied by 1.2, how much? Becomes 0.36, correct?
Mm-hmm.
So that one now becomes 0.36. And then here, earlier 0.3 multiplied by 2.1. Yeah? So multiply by 2.1 for V4. Oh, V4. Why it becomes 0.9 here? Is there any other thing that creating this 0.9? So this V5 still remain. Okay, this one. I know. This one have 2 arrow, that's why, right? So the V4 was 1.1, right? Negative 1.1 multiplied by 1.2 plus this one, yeah? 0.3 multiplied by 2.1. So that the total is negative 0.69. Because in V4 you have, look at these 2 arrow increase. Yeah, so you need to add the 2 of them. So that's why we have this, right? So we have the remaining V1, okay, and V2, and then this is the new numbers that you put. And then you continue the same manner, yeah? So this V4 earlier was how much? This one, yeah, 0.69, right? And then you multiply by negative 0.1, okay? That will add plus 1, so you will add with that, so become 1.06, yeah, negative times negative, right? And so on. So you retain the original poles and then plus with the other pools that coming to that node. Okay, is it clear or not?
Yeah.
So the question is, how are we going to compute this, right? In Excel, right? How are we going to compute this in Excel? Okay, so this is the updating formula. Okay? The new value of Vi at time t plus 1 is equal to the old value of Vi at time t plus with the pools, right? And Vi at time t plus 1, right? So that means the value of Vi is actually accumulated over time. Okay. So what is this value? the pools at Vi at time t plus 1, what is this? This is the summation of all j, yeah, for all the pools in Vj, right? That coming here. Okay. So how if we want to put the pools input simultaneously for all variable, not just one variable? Wow. Right? So in that case, you will use matrix formula, yeah? Matrix formula, because you want to have many input at the same time. So parallel. Okay. So what you will do, here it is. Okay. So actually it's simple. Using matrix now, suddenly everything becomes simple. Yeah? So let's make a pools vector as P. Okay, so you have n variables, so P1 to Pn. Okay. Now the value of the vertices at time t is V. Okay, so of course vector V consists of V1 to Vn. Same, right? Next. So the vertex value is updated by accumulation, right? So you have the vertex value at t plus 1 equal to vertex value at t plus Vt plus 1. Oh, now you have, what is this? A difference equation, right? This is recursion, you see, right? So what is this P, t plus 1? Of course, we know that this t plus 1 is equal to the sum of iji times pj. Yeah? Okay. So then you can update this. Yeah? So updating the formula in the matrix of this summation here is just the sum product. Yeah? This is just the sum product of all element P times the corresponding element in J column of the weighted adjacency matrix A. So we can put this together, okay, as this formula. So earlier, so the PT plus 1 here is just what? PT times A. Oh, now everything becomes simple, right? So what we have only two formulas. Number one is this. Vt plus 1 equal to Vt plus Pt. The second formula is Pt plus 1 equal to Pt times A. Okay? So, because of that, so we can combine. Okay, we can combine the two of them together. So Vt plus 1 equal to Vt plus Pt times A. So this is the formula that we will use. Okay, this is the formula that we will use. So this is difference equation, right? But in vector and matrix. Wow. So you see is this too heavy or you can follow? No problem? Joy? Devi?
Yeah, it's okay, I guess.
Huh? No problem, yeah? So this is the formula that you will use, just derive a while ago, okay? So now let's say you have initial value of the pools P0 and then initial value of the variables V0. So this is given by you, okay? So usually I put 0 and then this one I put something. Okay, and then the A, you already know, you already created, Livy just did a while ago. So then you need to know what is the meaning of 1 unit of change of the variables, right? So in that case, you give the meaning. Okay, let's try this a while ago, okay? And this is the meaning of 1 unit of change. Say 1 unit means, say 10% of the starting value of the variable pools plus 2 in Vj indicate the increase of the value by 20%, for example, right? And then negative 3, that means negative decrease of 30%. So this is just the meaning that we attach to it, okay? So using that, now we can simulate and to know the behavior of the system. Okay, so let's say I have an initial condition like this. Okay, if you don't like it, you can change this value because this is the one that given. So after that, you can calculate. Okay, now I have a P1 equal to P0 times A. So you get this vector. Okay, and then you calculate also V1 is equal to V0 plus P1, right? This one. Remember the formula a while ago. Okay, so and then now you calculate P2, you calculate V2 and so on. Okay, and finally you can draw the value. So this is what you count manually, okay, earlier. You can also calculate using Excel, okay. So what you will do, you create adjacency matrix, huh? Okay. So once you create adjacency matrix, what you will do, P0 here and V0 here is the one that you give. Okay, it's up to you to give. This is your input. Okay, this first row is the input. And then the second row and below is the one that you use formula. What is the formula of this? This is a P T plus 1 equal to PT, with this earlier, times A. Right? And then what is this V? This is VT equal to V earlier plus PT plus 1. Is this okay or not? After that, you draw. Huh? So over time, this is the behavior of the system. Can you make it? Can you make it? So I will show you in Excel. Okay, so first you create the adjacency matrix. I think you already did, right? And then what you will do, earlier at time 0, you can put yellow here. That means you can fill in anything, any numbers. Huh? This one also, you can fill in with any number. And then what is this? This is just multiplication, okay, of this with the A. Yeah? A is the adjacency matrix. Okay, just multiplication of this P with the adjacency matrix. And then what you will do, this one is just add. Yeah? Earlier plus the P. Okay, easy? Okay, so just copy this one. So this one is P5 plus earlier V5. Yeah? Same thing. So after you make this row, then you just copy down. Yeah? Copy down and then you draw. Yeah? What do you draw? What you draw is just V. Yeah? So this is the value of the V1 until Vn based on the drawing. Yeah? So eventually it will stabilize. You see the value is stable. Okay, it will not change after some time. Okay, you try first, and then if you have any problem, I can help you. So once you have CLD, okay, and then you can put any numbers there as the weight, right? And then you can simulate. You can start to see the behavior of the system that you model. Okay? The simulation is based on difference equation, which is very simple, right? It's affine, but in matrix. Yeah, really you need to make it. So once you make this, you share your screen. Even if you cannot, share your screen also, so that I can help you.
Oh, sorry, can I share my screen?
Yeah, sure, sure.
Okay, it here. After this, we move this
Multiply,
one.
yeah. And mul, yes.
Wait. Which one?
The earlier, the P.
The P?
P is all 5.
Oh.
It's an array.
Oh.
Comma.
Comma.
And then adjacency matrix. The whole adjacency matrix.
Oh, okay. So.
Okay, and then close it.
Yeah.
Okay, and then what you will do is, you know how to multiply matrix, remember? I hope you still remember. So highlight. No, you highlight everything.
Oh, yeah.
No, no, no.
And then
One row only. You highlight one row, okay, and then F2.
Yeah.
Shift
And
Control
then,
Enter. Shift Control Enter.
okay. Yeah.
Okay, good. And then this one is easy. The fee is easy. The fee is yes.
It's the same.
Yeah, no, this is just equal up plus left.
This one.
Yes, plus P1.
Plus
P1. Plus the
P1.
yes, that one. Enter.
Okay.
That one is just
so it's also
copy to the right. No, because this is not a matrix, so we just copy to the right. Okay, so
okay.
that one you copy per row down.
I need to
copy per row.
For this one.
No, you just copy the whole row. Copy. Okay, correct.
Okay, and then.
Okay, Control C, and then Control V there.
Oh, wait. Why is the dollar?
Oh, you not change. Enter. Okay. So because array cannot be changed, so you need to change. You get one.
Can I just name it?
No. Yeah, you can rename it if you want. That's fine. A. Matrix A or A. It's okay.
Okay.
And you name it. A. Enter. Again, you cannot change. You cannot change, but you can you can copy that, or you can make again that one.
Oh, okay. I will delete.
Mode.
So mode.
Yes.
Okay, so this one.
Earlier.
And then
Comma. A. Yeah, close.
Okay, and then
highlight. Only highlight. You highlight F2.
Wait. F2 and then
Shift Control.
Okay.
Good. And then just the same thing. You copy that P. And then copy that also.
Okay.
Good. So over time you can make it until 10 or 20. That's fine. So that you can see better behavior. Okay. So then you can start to draw the V. V1, V2, V3, and so on.
Okay.
Over time. So the y-axis, so you can put time here in column G. Be the time. Yes, 0 to whatever. So 1 plus, yeah?
Oh, wait.
1 plus.
Oops.
Earlier plus 1.
This one plus.
Okay, and then put it down. Okay, good. Now you can draw from the time until V5. G until I think you highlight first. You select yes, start, correct. Okay, very good. Yeah. You can select also including the name of variable so that you will know.
Okay.
From 9, yes. Okay, or that's
Okay.
okay, very good. So now you can see the behavior of the system. Now after that you start to change. Nah? If you want to change the behavior or the model, you can change. For example, the model you can change, right? The A matrix A you can change, and then the first initial value you also can change. Nah? The one that you can change, you can put into yellow, so that you will know. That one you can put as yellow. Okay, the same thing that one, yes, and then V0 also. Yeah, that one also yellow. Very good, excellent, very good.
Okay.
Oh, you make it! Wow! Right. So with this, you can create your CLD, okay, and then you can start to simulate your own system. Awesome.
Yeah.
Yeah. In fact, several company already make this and then they sell, as a software. Okay, just this one. Okay, of course they make it better graphical user interface, right? But the internal computation is exactly the same. Wow. Okay, super. I think it's time. Oh, okay, let me highlight the. Joy, how about you? Were you able to make it? Is it there?
Yeah. Suppose.
Joy, are you going to share?
Yes, sir. I just got disconnected. My internet's really, really bad today.
Yeah, yeah. So, do you want to share your screen?
I haven't gotten to try yet. I'll rewatch the recording. Because
Okay.
it was really laggy. Your voice was breaking up.
Okay, not clear. Okay, so you just watch the recording then. And try to really practice this, okay?
Okay.
Okay. So, okay, let me continue a little bit. We have 5 minutes. Okay, so once you make that simulation, can you see my screen now? Okay. Now you can change the initial condition, yeah, of the states. Okay. Example, you can change like this, and then the behavior will change, right? And you can also change the initial condition of the pulse. So this is, if I change the pulse something like this, then you see the behavior also change. Then in terms of stability, right? So here it is, the weighted graph, weighted T graph, okay, of the pulse is stable if and only if the eigenvalue of A, okay, has magnitude at most 1. Okay, so 1 is not the eigenvalue of A. So if you want to create a system that is stable, stable means it will not go up or go down. Okay, that means negative feedback loop. So you need to put the eigenvalue, based on the eigenvalue of the system, okay, A, then you can check the behavior. Okay, so for your case, I hope you can create your own system and then determine the weight and the sign, and then can you plot the behavior over time. Do you want to make a small project on your own so that you can have a practice? It's free, how many variables you want to create is up to you, and then what is about the system is up to you. So at least with this, you can be encouraged to try. Okay. Without practice, I think it will not become useful. Once you practice, then you start to feel difficult, right? Because of that difficulty make you stronger. Okay, so I will post, okay, an assignment for you to create a pulse model on your own. Okay, you can create any story. Okay, what is the meaning of this pulse? Okay, and then you can put any value also. Okay, and then you can use the same model, okay, and then explain what's the meaning of this behavior and so on. Okay, I think 2 weeks. Next week is holiday, so you have 2 weeks to finish the assignment. Okay, right. Okay, so thank you today. Yes,
sir, can you put it in Google Classroom instead of Lentera?
Can you just remember that I already said?
Okay, hopefully. Okay, thank you, sir.
because there is some monitoring from I think from Petra for this purpose. So yeah. Thank you very much for today. So see you.
Yeah, thank you, sir. See you tomorrow.
Okay, thank you, sir.
Thank you.